So, hello to all my young friends who are studying in intermediate and they are watching this video. Welcome to the lectures of GTK Academy. Continuing the chapter of motion in a plane, today we are going to discuss a new topic, our next topic, which is projectile motion. In our last video, we had discussed relative velocity. I hope that you would have seen that video. If you have not seen it, please do see that because that's a very important topic, and even from competitive exams point of view also, because a lot of questions are framed from that topic. Today we are going to discuss projectile motion. Since both these topics are very important topics, hence I am covering them in separate videos. Now, what is a projectile motion? Generally, if we throw anything or project anything in space where the force acting is the force of gravity, which is the predominant force, then we call it projectile motion, be it throwing of a cricket ball, a baseball, or you know, firing a cannon, all these things. Although there are certainly other forces like air resistance and all, but their effect is not that predominant, so we can neglect them. So only force which we consider during the trajectory is the force of gravity. Anyway, we are going to discuss in detail as we move ahead with this topic. So now, without wasting much time, let's start topic of today, which is projectile motion. However, before we start our topic, let's recall some coordinate geometry, or you can say curve tracing. Equation y is equal to kx square. This equation represents a parabola symmetrical about y-axis. Please note, we have the term x square here. Now, what is the equation of y-axis? X is equal to 0. The orientation of parabola represents whether k is negative or positive. Now, let me explain why I am discussing this topic, because we will be using this topic. Y is equal to k x square. That means x is equal to plus minus under root y upon k. Now, if k is positive, y has to be positive. Otherwise, whatever you have beneath this under root is going to become negative, imaginary. So y cannot be negative, first of all. Now this is our x-axis and this is our y-axis. So y has to be positive. That means y will only have value on positive side, and it can have the minimum value as 0. Now, the other thing which you notice, that for every y you have two values of x, that is x is equal to plus under root y upon k and is also equal to minus under root y upon k. That means for every y you have two values of x on either side of y-axis, one on this side and one on other side. For this value, one on this side and other on this side. For this value also, one on this side, other. So this curve is going to be something like this if you join the points. And here y is always positive. So it's a parabola, of this shape. So this is y is equal to kx square when k is positive. But if k is negative, what will happen? X is equal to plus minus under root y upon k. Now if k is negative, then y also has to be negative, otherwise something inside under root being negative will make it imaginary. So if y is also negative, these two negative multiplied will make it positive. So y will only take the values beneath this x-axis, that is on a negative side. And so if we have y is equal to kx square when k is negative, this will be the shape of parabola when k is negative. Now if we have equation like this, y is equal to ax minus bx square, a and b both are positive. Again we have minus negative term here. Here it is going to represent a parabola like this. Y is equal to ax minus bx square. Now let me just explain you why it is going to represent parabola like this. Take a very simple example. Y is equal to say 2x minus x square. A very simple example where it is easy for us to put it in any form. Just multiply by minus x square minus 2x is equal to minus y. Just add 1 on both sides, x square minus 2x plus 1 is equal to 1 minus y. That means x minus 1 whole square is equal to 1 minus y. Now just we are going to plot this curve x and this is your y. Now first of all we have to see from this equation where is it going to intersect with x and y axis. For intersection with x axis, put y is equal to 0. That means 2x minus x square is equal to 0. So x 2 minus x is equal to 0. So x is equal to 0 or 2. So we have 2 points of intersection with x axis 0 0 and 2 0. The other thing from here, if you see, x minus 1 is equal to under root 1 minus y plus minus. That means here for this term to be positive, 1 minus y to be positive, because negative will make it imaginary, y has to be less than or equal to 1. So if this is your 1, 0, 1, your curve y value has to be below this. So that means your curve will be below this and it will pass from 0 0 and 2 0, and since we have x minus 1 whole square is equal to 1 minus y, so it will be symmetrical about x minus 1 is equal to 0, that is x is equal to 1. So this is the line x is equal to 1. That means the curve is going to be somewhat like this. I hope you got a fair idea about this equation as to what it represents. Now since we are going to use this concept, that is the reason I have discussed it briefly here. I hope that many of you must have read it. But anyway, even for those who have read it, it's a revision. The other concept which I just wanted to recall is the concept of vector resolution. Suppose we have any vector, say v here, we can resolve it into two mutually perpendicular directions, which we normally do. Suppose this makes an angle theta here. So this is v cos theta and perpendicular to this is V sine theta. Now if theta is equal to 90 degree, what happens? V cos 90 is equal to V into 0, that's 0. So that means there is no component of V perpendicular to that. So if we have a force like this, so in this direction, which is inclined at 90 degree to force, there is no component of this F, because F cos 90 is equal to 0. So what happens to F sin 90? F sin 90 is equal to F, this one only. So this is one concept which we are going to use. Now let's start our topic, projectile motion. When a body moves such that acceleration is parallel to direction of velocity. Suppose a body is moving in this direction and it has a velocity v, and we have acceleration parallel to this. Say we have acceleration a like this, or it can be like this in negative direction, that is retardation. So if we have this one, then what is it going to do? It will increase the velocity. However, if we have this form of acceleration, which is retardation, what it will do? It will reduce the velocity. That's it. However, in both the cases, none of them, whether it is this or this, they will only increase or reduce the velocity. That means increase the magnitude or reduce the magnitude. But they are not going to change the direction. The direction of velocity will remain same. So when a body moves such that acceleration is parallel to the direction, magnitude of the velocity changes, direction remains unchanged. It's a very, very important thing. In this case, we call it straight line motion. This is straight line motion, which we had discussed in the previous chapter. But when the body moves such that direction of acceleration is different from that of velocity. Suppose you have velocity in this direction and your acceleration or force is in this direction, because acceleration is there, that means the force is there. If you have a case or scenario like this where direction of acceleration or force is different from the direction of velocity, what will happen? Magnitude, of course, yes, it will change. But one more thing will happen, direction of velocity will also change. And here the body, instead of following a straight line path, will follow a curved path. Now let's see how it happens. Suppose we take our x and y axis like this, and we have a body. Its position is shown by this yellow dot. It's given v velocity in this direction. Now if we have a force or acceleration, whatever you call, in this direction, here you can see the direction of force or acceleration is different from the direction of velocity. So the path in this case has to be curved. The velocity will change in magnitude as well as direction. Now let's understand how it happens. Let me give you some idea so that when we'll be using that, you won't face much problem. Now suppose this force is not there, and this is the position initially at time t1, say x1 and y1 are the coordinates. Now since there is no force, what will happen? The body is going to follow a straight line path shown in this green color. Now you just resolve it into two components, Vx and Vy, in the direction of x-axis and in the direction of y-axis. Now this component will move the body in this direction, that is y-axis, and this component will move it in x-axis direction, and these both motions will be independent because they are at 90 degree to each other. So there is no component of Vy in direction of Vx or Vx in the direction of Vy. So after some time, say its position is shown by another dot here, and we say this is at time t2, it is x2 and y2. Again at time t3 it becomes x3 and y3. At time t4 it becomes x4 and y4. Till now there is no force. Now the force comes into picture. Now you can clearly see that the force is in the direction of x-axis. So there won't be any component of force in y-axis direction, because we have already said that there is no component in the direction perpendicular to the vector. That means this component of velocity will remain unchanged and only Vx is going to change. Since there is an acceleration in this direction, so Vx is going to increase gradually and gradually. Suppose we had started at t0, that is t1. After some time, when force comes, this x2 will change. So it will be a bit more. However, y2 will be same because the velocity in direction of y-axis is same. x3 will be further increased like this. Instead of x3, at t3 we'll have this one, and instead of x4 at t4 we'll have position shown like this. Now if you join all these dots, purple dots, you will get a curve. So now the body is following a curved path, and here straight line. I hope that now you are all clear with this as to how the body follows a curved path. The best example of this is projectile motion. So let me give you an example of projectile motion from day-to-day life. Suppose we have a body like this, and this is projected upwards with a velocity u in this direction, making an angle with horizontal. Now what is the force or acceleration here? That is the acceleration due to gravity. Now you can see that acceleration is not in the line of velocity. It has a different direction. So what happens? You all must have seen it, that the body follows a curved path like this, shown in yellow color. This is the trajectory. Now just what we had discussed a couple of minutes back, that parabolic curves, I think if you remember. Now you can understand the reason why I discussed them. The trajectory here is parabolic curve. Now this we can see, and I am going to prove it also in the coming slides as to how this trajectory is a parabola. During the trajectory, the velocity is going to change, be it in magnitude or in direction. Now, your velocity is in this direction, and this is the trajectory. So you will have, at any point, you will have different velocity. And if you want to find velocity at any point, what we have to do, we have to just draw a tangent here. This tangent will give you the direction of velocity at any point. Like this, like this, like this. So velocity is going to change in magnitude as well as direction. So tangent at any point gives the direction of velocity at that point. Suppose at this point you have u2, at this point you have u1. These all are the direction of tangents at that point. You can see, it can be seen from the figure. Now, projectile motion can be resolved into two simple motions. Instead of us analyzing a curved path or being confused with that kind of motion, we can resolve it into two simple motions, horizontal and vertical. Why? Because they both are completely independent of each other. Suppose this is the velocity u which you have given to projectile, and it makes an angle theta with horizontal. So the velocity in horizontal direction is u cos theta and vertical is u sin theta. Now what is the force or acceleration here? It is g in this direction, vertically downwards. Now g is opposing u sin theta, and there is no component of g in x-axis direction because it is perpendicular to, you can't have a component of g in this direction because this is 90 degree, or in this direction because this is also 90 degree. So you will not have any component of g in the direction of u cos theta, and g is in the direction of negative y-axis, negative y direction. That means g is only going to affect u sin theta. In fact, it will be a retardation for u sin theta. But for u cos theta, it will not have any effect. That means the horizontal component will remain unchanged. So horizontal component of velocity remains unchanged. This is a very, very important thing. Now let's understand by a different method also how horizontal component of velocity remains unchanged. Now suppose you have a velocity u in this direction and you have acceleration due to gravity in this direction. Now definitely it is going to reduce the velocity. Suppose after some time the velocity at any point is u dash. Now what is the reduction in velocity? Now reduction in velocity is u vector minus u dash vector. This is the reduction in velocity, you can say delta u. Now just draw u and draw minus u dash. So this is minus u dash. Now add them. So this is u minus u dash shown by this red arrow. So this red arrow indicates delta u, which is the reduction in velocity. This is the reduction in velocity. Now just see here, when it is started, it has a horizontal component in green color. At this stage, this remains same. There is no change in horizontal component of velocity. However, when it is started, it has a vertical component shown in blue color. This vertical component is reduced because we told that Acceleration is in vertical direction. There is no acceleration in or force in horizontal direction. It's not going to affect. Now, this is the initial uh, vertical velocity, and this is the vertical velocity at this point. Now just draw both these arrow at the same place. That means what is the reduction? Initially the vertical component was this much, now it is this is small. Now just add this red arrow. Now it becomes same. That means this red arrow is the reduction, and reduction only happens in vertical direction. Suppose this red arrow, instead of like this, had it been like this, say, suppose, then you would have reduction in horizontal direction, this component, and vertical direction, this component. But you don't have here. This is actually, in fact, I am drawing as if I am taking the velocity exactly at those moments. But however, if you have the data, you will get this same kind of figure. That means what happens? When the body starts, it has a horizontal component and a vertical component. After some time, horizontal component will be same throughout. Vertical component will reduce. Here you can see, here it was this much, now it has reduced. As the body goes up, it will reduce further, and when the body reaches the highest point, then there is no velocity in the vertical direction which will take it upwards. That is what we mean. It has reached the highest point. So then this component becomes, blue one becomes 0, and we have only green color here. Now you can see this is the resultant U of both this component, green and blue. Here you have this resultant of both these. At this point you have this resultant of green and blue, but at this point there is only one green color arrow. So that is the horizontal velocity as well as the resultant at this place. Then the body starts coming downwards. So vertical component will be in the downward direction like this. At the same height, suppose this is same, you will have the component exactly whatever you had here, you will have the same here in the downward direction. And as it moves, it increases in the downward direction, and finally it reaches a point where the velocity again becomes u, but in this direction. Initially you had u in this direction, now you will have u in this direction. As you have horizontal component unchanged, the vertical component, whatever you have here, you have just opposite or reverse of that here. I hope that you are clear with this. Now let's move to some definitions. When a body is projected with a velocity u making an angle theta, this is the horizontal component ux, vertical component uy. It follows this trajectory shown in yellow color, and this is the height h, and this is the distance covered r. Now what do we call all these? U, we call it initial velocity. Ux, horizontal component, which is u cos theta. Uy, vertical component, u sin theta. H, maximum height. R, the distance covered by projectile, we call it range. That is the horizontal distance covered. However, there are certain assumptions also. What are they? Air resistance is considered to be absent. Although when you throw any ball in this direction, there is bound to be air resistance, but that is negligible. So we neglect it, and apart from that, it makes our calculation complex also. So since it is not predominant, we neglect it. So air resistance we consider as absent. Effect of earth curvature is also considered negligible, because you are throwing a projectile like this, it's going to follow a trajectory like this. Here